14.8. Other applications of fluid dynamics. The outline of this video is as follows. We will explore the physics behind how objects fly, focusing on the concept of aerodynamic lift. First, we will cover the fundamental principles of lift, explaining how an upward force is generated to counteract gravity. Next, we will examine the key factors that influence the strength of this lift force, including an object's shape, its speed through the air, and its orientation. Finally, we will investigate the important role that air density plays in achieving flight. Understanding these concepts will help explain not only how airplanes stay aloft, but also the interesting behaviors of objects like golf balls and baseballs as they travel. We can understand the lift force that keeps an airplane in the air using two different but related physical principles. The first perspective uses Newton's third law. As an airplane moves forward, its wings are angled to push the oncoming air downward. Because for every action, there is an equal and opposite reaction, the air must in turn exert an equal upward force on the wings. The second perspective involves Bernoulli's principle. The top surface of a wing is curved, which forces the air flowing over it to move faster than the air flowing underneath. Bernoulli's principle states that faster-moving fluid has lower pressure. This pressure difference, with higher pressure below the wing and lower pressure above, creates a net upward force. These two explanations are complementary and both contribute to the overall effect. The total force from the air on the wing is resolved into two parts: a vertical component we call lift, and a horizontal component opposing motion which we call drag. This diagram illustrates the two primary aerodynamic forces that act on an airplane wing as it moves through the air. As you can see, the wing's curved shape and angle cause it to deflect the oncoming airstream downwards. This deflection is a force exerted by the wing on the air. According to Newton's third law, the air must therefore exert an equal and opposite force back on the wing. This upward acting reaction force is what we call lift. At the same time, the air also resists the wing's forward motion. This resistive force, which always acts opposite to the direction of velocity, is called drag. In summary, a wing generates an upward lift by pushing air down, while simultaneously experiencing a backward drag force from air resistance. Now that we understand the basic origin of lift, let us break down the specific factors that determine its magnitude. This is essential for designing and controlling an aircraft. First, lift depends on the speed of the object and the area of the wing. A higher speed or a larger wing surface means the wing interacts with more air, which can generate a greater upward force. The shape and curvature of the wing are also crucial. This special shape, known as an airfoil, is designed to optimize the pressure difference between the top and bottom surfaces. Another key variable is the angle of attack, which is the angle between the wing and the oncoming airflow. Increasing this angle slightly can increase lift. Finally, lift depends on the density of the fluid itself. For example, an airplane generates more lift in the denser air found at sea level compared to the thinner air at high altitudes. However, if the angle of attack becomes too large, the smooth airflow can become turbulent, causing a sudden and dangerous loss of lift known as a stall. In summary, the amount of lift is a dynamic quantity determined by speed, area, shape, angle of attack, and fluid density. Let us connect our physics principles to a practical aviation challenge. Taking off from a high-altitude airport. The amount of lift a wing can generate is directly related to the density of the air it moves through. A great example of this is in Denver, Colorado, which is known as the Mile High City, because it is located at an altitude of about 1,610 meters above sea level. At that height, the air is roughly 15% less dense than it is at a coastal airport. To compensate for this thinner air, an aircraft must achieve a higher speed to generate enough lift for takeoff. Reaching this higher speed requires the plane to accelerate over a greater distance. Therefore, airports at high altitudes must have longer runways than airports at sea level. The concept of aerodynamic lift is not just for airplane wings, it is also crucial in many sports. Let us examine the fascinating case of a golf ball to see how this works. When a golf club strikes a ball, it imparts a very rapid backspin. The small indentations on the ball, called dimples, play a critical role. These dimples increase the surface roughness, which allows the spinning ball to more effectively grip the air flowing past it. As the ball spins backwards, this enhanced grip deflects the air downwards. Following Newton's third law, because the ball exerts a downward force on the air must exert an equal and opposite upward force on the ball. This upward force is the lift. This effect might seem counterintuitive. While the dimples do increase drag, the amount of lift they help generate is far more significant. The additional lift keeps the ball airborne longer, allowing it to travel a much greater distance than a smooth ball ever could. The aerodynamic force of lift is not just for airplanes. It also explains the physics behind a curveball in baseball. When a pitcher throws a curveball, they impart a rapid spin to the ball. The raised stitches on the baseball's cover are crucial, as they create friction that allows the spinning ball to grab a thin layer of air and drag it around. As the ball flies toward the batter, this rotating layer of air deflects the main airstream to one side. According to Newton's third law, for every action, there is an equal and opposite reaction. Therefore, the deflected air pushes back on the ball with a force in the opposite direction. This continuous sideways force is what causes the ball's path to deviate from a straight line, creating the characteristic curve that can fool a batter. Let us bring together the key ideas we have discussed about aerodynamic lift. The fundamental concept is that lift is a force generated when an object changes the direction of a fluid flowing past it. We can understand this force through two complementary physical principles. From one perspective, Newton's third law tells us that if a wing pushes air downward, the air must push the wing upward. From another, the Bernoulli effect explains how differences in fluid speed above and below the wing create a pressure difference that results in a net upward force. The amount of lift an object generates depends on several variables, including its speed, surface area, shape, and its angle relative to the fluid flow, often called the angle of attack. The density of the fluid is also crucial. This is why aircraft at high-altitude airports, where the air is less dense, must achieve higher speeds to generate enough lift for takeoff. Finally, these principles extend beyond aviation, explaining the behavior of objects in sports, such as the extended flight of a dimpled golf ball or the sharp break of a curveball. To wrap up, let us apply the principles we have discussed to two practical questions. These scenarios will help you connect the concepts of lift, density, and fluid interaction to the world around you. First, think about air travel. Why does an airplane require a longer runway for takeoff at a high-altitude airport, such as Denver, compared to one at sea level? Consider the relationship between atmospheric pressure, air density, and the speed an aircraft must achieve to generate sufficient lift. Next, consider the design of a golf ball. A ball with dimples travels significantly farther than a perfectly smooth one given the same initial hit. Explain how these dimples, combined with the ball's backspin, work to generate an upward lift force that counteracts gravity and extends its flight. Pause and consider how you would answer these questions. They are excellent tests of your understanding of fluid dynamics in action.